Hello everyone, my name is Mitja Žalik and I'm a PhD student at the University of Maribor, Faculty of Electrical Engineering and Computer Science. Today I will talk about time efficiency of various move-to-front implementations. So in various applications, self-organizing lists are used to improve the efficiency of searching for the elements. The frequently used element strategies in practice are the counting strategy, when the elements are sorted according to the frequency they appear in the data stream. Transposing strategy, where each element is swapped with its predecessor in the list after being located, and the move to front strategy, where the element is moved to the front of the list after being found on the list. Move to front transform is used the most frequently of all, because in data compression it can reduce the information entropy and thus improve the compression ratio. Excuse me. So to define the move to front transform, we first have to define the stream of symbol denoted by S, which contain n symbols from the alphabet sigma with the cardinality of m. For the move to front, we first have to create a list L, which is initially filled with the characters from sigma in the alphabetical order. And after that, move to front or MTF processes symbols from the stream S sequentially. At each iteration, the it symbol SI is found in list L. Its position J is sent to the output F. And after that, SI is moved to the beginning of list L, while the positions of elements before position J are increased in the list. So here we have an example where on the top of the table we can see the input stream S, and in the vertical direction we have the state of the list L in each iteration of the move to front transform. So initially the elements in L appear in the alphabetical order, and then we start with the first iteration of the move to front transform, where we find the symbol B in the list. It's in the position 1 initially, so we put index 1 to the output F, move the symbol B to the front of the list L, and move all elements before B one position down in the list. So in this case, the new state of the list L is BACD. After that, we move to the second iteration of the MTF transform. Now we have, now we are searching for the element D, which is in position 3 in the list. So to the output, we will send index 3, move the element D to the front of the list, and all the elements before D will be moved one position back in the list L. So the new state will be DBAC. And so the iterations go on in the same way till the last character of the input stream is being processed. Here we can see that the patterns of the same element will produce the sequence of zeros in the output stream F, and the patterns of alternating characters will produce the sequence of ones, as can be seen in the example. In this way, the entropy of the data can be decreased, So in the example, the entropy of the input stream S is 1.69, and the entropy of the output array F is 1.36, which is of course considerably lower, and this would help with the compression ratio, of course. So because searching and moving the elements in the list L has to be done for each symbol from the output stream that is being compressed, the main motivation is that if this is done efficiently, the whole data compression algorithm will be faster. Therefore, our goal was to find the fastest implementation of the MTF transform on different computing platforms. We compared 4 implementations over the 3 different computing platforms and with 2 different data distributions. So in the continuation, I will at first present or tested or reference implementations. The first one is denoted with MTF-A. It's written in plain C language. At first, for each symbol Si, its position J in list L is found with the simple while loop. After that, all symbols before position J are moved up in list L by 1 place. This was done with the help of for loop. And at the end, the symbol Si is set at the first position of the list with a simple assignment. So here you can see a C code of the MTF-A reference implementation. The second implementation, MTF-B, used the functions from the C library. Functions for string manipulations were used in this example, in this implementation, and that is the most common implementation found on the web. It uses an auxiliary list L auxiliary. At the beginning of each iteration of the MTF, list L is copied into L auxiliary using function strcpi. After that, Si is found in L auxiliary using function strchr. So its position J is found like it's visible in the code. And after that, J-1 elements are copied back to the list L using function strncpi. And finally, symbol Si is moved to the front of the L, again using simple assignment. So the code is shown here. Third implementation, MTF-C, is practically the same as the MTF-B. We just replaced the functions strcpi and strncpi with the function memmove from the C library for copying the data between L and L auxiliary. So here you can see the code for the third reference implementation. And the last implementation, MTF-D, uses the functions from the C++ standard library, where at first we determine the position of the symbol Si using stdefine function. Afterwards, we move the elements in list L by 1 position using the copy backwards function. And at the end, again, we use simple assignment to set the search element at the first place in list L. So here you can see the code for the last reference implementation, MTF-D. All of the implementations were tested with 2 different data distributions. In the worst case distributions, symbol in stream S are arranged in a way that the search element Si is always the last in list L. So all elements in L must be moved in each iteration, which brings us to time complexity n times m, so the number of elements in the stream times the cardinality of the alphabet. And the second distribution is the expected data distribution, where we use the textbook book 1 from the standard Calgary corpus. So all implementations were tested on 3 different computing platforms, P1, P2, and P3. P1 was ran on 64-bit CPU-based hardware with complete instruction set with the Windows 10 operating system, and the code was compiled using MCVC compiler version 9.23. Second platform used the same hardware, but ran on the Debian 10 Buster operating system, and the code was compiled using GCC 8.3.0. And the third platform, P3, used 64-bit ARM CPU with reduced instruction set and run on the Raspberry Pi operating system, which was based on the Debian Buster, and code was compiled with the GCC 8.3.0 compiler. So P1 and P2 were run on standard PC computer with Intel Core i7 processor and 16 gigabytes of RAM. And platform P3 was run on the Raspberry Pi Model B. So of course it's senseless to compare the running times of the MTF between different platforms directly, but we were interested to know how efficient are different implementations on each platform separately. So at first we have the results for the worst case data distribution on the platform P1, which is, to remind you, Windows 10 operating system. Here, the most efficient implementation was MTF-C, and the least efficient was the MTF-A. It's interesting to see that MTF-B was almost the least efficient implementations, much less efficient than MTF-C. And if you remember, the MTF-B was almost the same as MTF-C. We just used string copy functions in the MTF-B and mem-move in MTF-C for moving the elements between list L and auxiliary list L auxiliary. So for the expected data, the results are completely different. Here, the most efficient implementation was MTF-A, and the least efficient is again MTF-B. In the second computing platform, for the worst case data, the results are very similar to the platform P1. Again, the most efficient implementation was MTF-C, and the least efficient was MTF-A. The only bigger difference is that MTF-B, the third most efficient implementation, was very close by running time to MTF-D implementation on this platform, but almost as bad as the worst implementation, MTF-A, on the platform P1. When using the expected data, again, the results are similar to the platform P1. The most efficient implementation was MTF-A, and the least efficient was MTF-B, and the order of all implementations by efficiency remained the same as with the P1 platform. If we move to the platform P3 with the reduced instruction set, again, we can see very similar picture. MTF-C implementation was the best performing, and MTF-A was the least efficient when using the worst case data distribution. With the expected data distribution, again, MTF-A was the best, and the least efficient was MTFB. Here MTFD, so the implementation with the functions from the C++ standard library, was almost as efficient as implementation MTF-A. So to summarize the results, the pattern of algorithms properties is common regardless of the platform we used. MTF-A was the slowest on worst case data, but the fastest with the expected data. MTF-B was always the worst or second to worst, and MTF-C was the fastest on worst case data scenario and the third most efficient on expected data, regardless of the platform. And MTFD was always the second best implementation, commonly just a little bit slower than the most efficient implementation, regardless of the data distribution. So we can say that MTFD is the safest choice if we have no idea what the data distribution will be for our use case. So to conclude the presentation and to point out the findings, we compared four different implementations of the move to front transform, which is a very simple algorithm, and the implementations were relatively short and similar between each another. But even though we measured very large differences in time efficiency, because the least efficient implementations were up to 5 times or took up to 5 times more time than the most efficient implementation. So of course, for every critical routine, you should test performance and evaluate it on the real data and on the target hardware that will be used on the production environment. Thank you for your attention.